inherent compassion of a self-organizing universe, for me it's easier to talk about compassion than it is to talk about love, because there's conditioning there. That's a separate thing. So you'll see why. And there's some other phrases in here that I stole from some other people, some of whom are in the room. So this is sort of the map of what I'm going to try and talk about. It starts because I'm a Buddhist practitioner, so, okay, full disclosures, Jewish practice, senior Zen student at the Village Zendo in New York, the last 7 years a surprised shamanic initiate, so all this stuff is going on in here. And for this sort of presentation of this material, if you've seen me talk here before, a lot of this material will be familiar because the core of it is essentially the same. But where it starts and where it finishes and what branches off of it, there's multiple, infinite potentially, ways of looking at it. So this is how the lens I'm going to look at this through today. And in Buddhist practice, we talk about two pillars of practice. There's wisdom and compassion. Wisdom, seeing things as they are for real without delusion, unmediated by our own conditioning, etc. And then compassion, which I hope we'll arrive to at the end of the talk. To get there, we're going to get kind of sciencey, which I feel emboldened to do because this is science and non-duality, so one should expect both, yes. And I'm going to introduce you, if you don't know about it, to the ideas of complexity theory. So complexity theory is about systems of interacting things that are called complex systems, and they are self-organizing, and they are adaptive. So they're living things that respond to a changing environment. And the way this is one way of defining them. They are groups of interacting individuals that if they fulfill 4 criteria, they organize themselves from the bottom up into larger scale structures, and those larger scale structures often appear as though they are planned from the top downward, but they're not, and that's a key thing. These structures are often referred to as emergent self-organization, or if people talk about emergent properties as a technical term, this is what they mean. In a bottom-up way, unplanned things are arising that look as though they were planned. And they are adaptive. That's a key essential thing, so that they can change they can change in response to a changing environment. So, examples. This is one way of looking at economic markets, urban development. If you're familiar with the work of Jane Jacobs and how cities grow, she was thinking in terms of complexity theory even before the theory was fully cohered and had a language. I came into it because I was collaborating with an artist who taught me about this when I was doing stem cell research 20 years ago, and that stem cell research says something like this. So if you look on the left-hand side, you see that open oval. That's like a stem cell, and it could be an embryonic stem cell or an adult stem cell, and when it divides, it replaces itself, so stem cells always replace themselves, but the other cell becomes a differentiated cell. It turns on different genes, so it's now functioning in specific ways that are appropriate to the tissue for which it's intended. That cell then divides, those cells divide again, and at each stage, different programmed genes turn on and off until finally, on the right-hand side, you get all the mature cells of your body. So bile duct cells, hepatocytes in the liver, all the white blood cells, every organ has its own set, and those are called terminally differentiated cells. And this was always thought for about 100 years to be hierarchical and unidirectional. It went from left to right, and things followed these arrows. There were no other possibilities. And then my group's work and a few others in 1999, 2000, this eventually won the Nobel Prize for cell plasticity, showed that, but I didn't get it, showed that in fact all these different things could happen. Cells, intermediate cells, progenitor cells could become stem cells again, cells could cross boundaries, some cells could go back along their lineages, and if you look at the bottom, a terminally differentiated cell going all the way back to an embryonic stem cell, that was proven in principle by the cloning of Dolly, which I thought I had my picture of her here, but I don't. I got to meet Dolly. That was even better than coming to Sand. And you can meet her too, because she's stuffed in the Museum of Natural History in Edinburgh. I know. But she was quite great. You can also use it to describe ant colonies, and it's much easier and intuitive to talk about ant colonies to start because everyone here knows ants. Everyone in the world knows ants from when they're kids and the strange, interesting things that they do. So, for example, ants form food lines. And if you look at it from a distance, it looks like a straight line, and the ants are going from the food source over there to the ant colony over there, and they're moving back and forth with purpose. No one planned the line. How does the line form? It forms because ants lay down 9 different possible pheromone signals that they can sense from each other, and they interact through touch as well. And out of those interactions, they know what choices to make, and they start to form lines, for example. So an ant that has picked up some food changes its pheromone scent so that another ant encountering its trail turns in the direction of where it's coming from and finds the food, turns around, and that starts to build the line, for example. Now, all complex systems fulfill certain criteria. Number one, numbers matter. So 3 ants don't make a colony, but 8 ants do. Because if you have a 25-ant ant farm from mail order, which my nephew kept buying me for a while because he thought I was obsessed with ants, which I was. They continue to self-organize tunnels, food lines, and cemeteries until they get down to around 8 ants, and then they are only doing tunnels and food lines. And at 3 ants, the 3 ants are just wandering around by themselves. 25 ants is not as complex of a colony as 250 ants, which isn't as complex as 2,500 ants. And since what applies to ants applies to any complex system, including people, a village is not a city, is not a megalopolis. With increasing size, you get increasing complexity, increasing diversity of interactions, etc. There have to be negative feedback loops balancing the system, homeostatic feedback loops. So think like an air conditioner. The room gets too warm, the air conditioner turns on. The room cools down. If it gets to the bottom level you'd set, it turns off. And so it keeps it oscillating in this homeostatic zone. You can have positive feedback loops, such as if a room gets warmer, the heat turns on, and so it gets warmer and warmer and warmer. But they can't. But the overall balance has to be negative feedback loops with homeostasis. You can still get self-organization with positive feedback loops, except they tend to be energy expending and self-limited. So think tornadoes, hurricanes, cancer, in terms of the cell biology. Interactions are local without global sensing. There's no ant in the colony that's planning everything that's going on or monitoring everything that's going on. The queen ant only serves a reproductive function, and she's as much a part of this web of interactions as anyone else. Similarly, in human societies, anyone who claims to be at the top planning things doesn't really work out for the long term. Low-level randomness. This is, to me, one of the most interesting things. If there's too much randomness in the system, then you can't get any self-organization. You just have, molecules bouncing in a gas. Too little, though, you might get some self-organization, but if the environment changes, how can it change how it's going to respond and self-organize in response to the changing environment? It can't. Then it's become, without any randomness, then essentially it's become like a machine, always doing exactly the same thing. So you need this low level of randomness in the system, which allows for the exploration of new possibilities. And that's referred to as quench disorder in the jargon. So when you look at a food line like this, if you bend down and look more closely, you see that in fact not all the ants are following the food line. There are a few ants, 2, 3, 4%, that aren't following the food line. If you put your foot down in the middle of this food line, the ants that aren't in the line are the ones that will rapidly find the quickest way around your foot. If the food source runs out, these ants are the ones that are off finding other food sources. So you need a little randomness in the system to explore new possibilities and organize to respond to those changes. And then we realized in the same way you can look at cells, which fulfill all the criteria for members of a complex system, interacting with each other in all the ways that we talked about. And if you look on the left, you see the old view of the hierarchy, unidirectional and hierarchical. But when, with our new techniques 20 years ago, we looked more closely at what was going on, we in fact saw that a small number of cells were going in directions that weren't expected. So that was an example of quench disorder in the system. So this has implications. First is that if you have cell lineages creating bodies in an organized way, Mass extinction events in any complex system are necessary. What do I mean by that? You can draw this kind of map for the concepts of order and disorder in the universe. Perfect order is like billiard balls hitting each other, or perfect crystal formation. Disorder, like molecules in a gas. Chaos, we're talking fractal organization, self-similar all the way down. And if you look at where mathematically complex systems lie, they lie here, along the border of chaos, between order and chaos. So you'd think you could plant, mathematically, any complex system could be plotted to some point in that system. But because of the quenched disorder, that's not true. It sort of wanders around in that zone. And given enough time, inevitably, it will wander outside of that zone, and it will undergo a mass extinction event. And so that means that the price of adaptation, the price of being alive, means necessarily you will die. There. Which is a relief. When I give this talk in front of doctors, there's usually sort of like a relief. They're kind of off the hook. But then this gets us into some more interesting territory. And this is what happens with hierarchies of complex systems. So what do I mean by hierarchies? We've already seen the ant colony, and the ant looks like a solid thing on the ground from a distance. It may be moving, but it looks solid. When you go up close to it, you see, oh, it's not a thing at all. It's actually just ants in this intricate dance as they're interacting with each other. Well, if you go up closely to my sort of scale, at the microscopic scale, the ant disappears, and it's just a bunch of cells interacting. So whether something appears like a thing or a phenomenon arising from smaller things depends on the level of scale you're observing it. Is it an ant, or is it a community of cells? Is it a colony, or is it the individual ants? And so that depends on the scale of observation. And so you can look up in the sky and see a murmuration of starlings, and it looks like this thing, this shape. But if you know what it is, you're not puzzled. You go, oh, that's a bunch of birds. But if you go to the bird itself and look at that closely, that's just a flock of cells, self-organizing to look like a bird. And my finger pointing at the birds looks like a finger at this level of scale, but it's just a community of cells that's organizing itself to look like a finger pointing upwards. Bait balls of fish. It looks solid from afar. Up close, it's just fish. The fish looks solid from afar. Up close, it's just cells. And in case of humans, 90% of our cells aren't even ours. They're bacteria, without which we wouldn't be alive. So what is your body at the cellular level? Manas Kafatos and I have written about this a lot and refer to this as complementarity, like this image. Is it two faces, or is it a vase? A complete description requires that it is both. But you can't, in fact, see both at the same time. People have studied this with fMRI. The best you can do is move quickly back and forth between them. So you can only see one. You have to choose a perspective, and that excludes the other possibility at the moment of observation. But you can change your perspective. And so cells are self-organize into bodies, which self-organize into communities, and depending on what you call a body, you get different kinds of communities. But what about cells? Are they some sort of fundamental thing? Well, cells are just nothing more than biomolecules organizing themselves in water. And this has implications for where is your boundary. At this level of scale, my boundary is my skin, and we are separate beings bounded by our skins. But at the cellular level, every time you have shaken someone's hand, hugged them, kissed them today, you've exchanged some of your microbiome. And in fact, if you live with anyone at home, including your pets, you share a single living microbiome that's a single entity. Within a few days, everyone's microbiome sort of flows into everyone else's. So at the cellular level, your boundary is actually kind of the room you're in. At the molecular level, well, I'm breathing out CO2, and the plants are breathing that in, and they're breathing out oxygen, and I'm breathing that in. So at the molecular level, where is the boundary, right? Biomolecules, they're just nothing but self-organizing atoms. At the atomic level, there's no atom in your body that you didn't eat, drink, or breathe from the planet. So we usually think of ourselves as living beings that sit on the planet, but it's just as reasonable to say, complementarity, that we are the planet that has self-organized its material into beings that think of themselves as separate. So when we sent Curiosity to Mars, There are some really brilliant engineers at NASA who figured out over decades how to send a robot to Mars and send images back to us, which is awesome. And that's absolutely true. But you could also, just as reasonably true, say that it took 3.5 billion years for Earth to figure out how to reach Mars. We're nothing but walking and talking Earth. Atoms are nothing but subatomic particles, and those are smaller subatomic particles, and then you get down to the smallest thing. There is a limit at the Planck level, and those may be strings or some other thing, depending which theory you have. But whatever theory you have about that, in general, there's sort of agreement that these just emanate out of what's called the quantum foam. That space-time is an energy-rich vacuum that is continually, all that energy is continually popping off into mass, E equals mc squared. Often in matter-antimatter pairings, so they self-annihilate and turn back into energy. But if they manage to persist, then they can interact with other things like themselves, maybe strings, and those interact and become subatomic particles, and those become atoms, and those become molecules, and the whole universe springs into existence. There's no point there where a thing is a thing. Even at the lowest level of scale, it's just matter and energy exchanging. So the thingness in the universe doesn't exist. And the thing I said about boundaries is also true, all the way down, because on the quantum level, what's the boundary of a quantum particle? The entire universe, non-locality. So at the smallest level of scale, the boundary is everything. So we don't live in the universe. The universe isn't an empty box. It's not a place in which we reside. We are, in fact, the universe, arising, emanating from its substance, within itself. And this correlates nicely to Buddhist concepts of the relative and the absolute. And in this regard, so far, this is all in keeping with the main lines of Western philosophy, all of contemporary science. I haven't said anything that traverses that. This notion that it stops at space-time is where it becomes a little more interesting. And if we expand a little bit, and you can diagram it this way, with the bottom, the quantum vacuum arising from space-time, basically, the energy-rich vacuum. But Minas and I wrote a paper a couple of years ago called Fundamental Awareness. We're talking about a fundamental awareness model where we both have contemplative practices and say that the metaphysics that arises from experiential practice in all these traditions, for example, which we only cite here, I'm only citing here because these are the ones we talk about in our paper with which we have personal experience. If you look at this, then you have data that isn't incorporated into the system. And what that data means is that there's something below space-time. And we would call that non-dual, pure, fundamental awareness. And that's sort of a side thing, but an important side thing. And this is perfectly in keeping with Western philosophy and Western science. There's nothing here that traverses that. In that paper, we finish, if you know the hard problem of consciousness, we said a proper understanding of human qualia, the experiences in consciousness, reflects that are the foundational nature of all existence. All views and all experiences, every field, every wave particle, every atom and molecule, every living and non-living aggregate of such, anything and everything observed, experienced, or imagined is in fact nothing but qualia within the fundamental awareness that is the ground of existence. So, final step, we'll skip this stuff. There's lots of papers I've written about this, so it's not hard to find. But we can sort of look at all Buddhist metaphysics, and it sort of maps to this very cleanly. Luriana Kambala is also very easy to draw parallels. Vedanta philosophy, Kashmiri Shaivism also. But the final thing, back to this wisdom compassion thing. To me, science is one of the best tools we have for gaining wisdom, to see things as they actually are, freed from our delusions, including just what the normal boundaries of our senses are. We can do scientific practice to see the way the world actually exists. And one of the ways it shows us is this model that I've shown you, that the entire universe is a bottom-up, self-organizing system. Where does compassion come into this? Well, here we are, these bounded little things, very tiny, and there's a whole bunch of us gathered in this room, and we're all separate from each other. The thing about boundaries is that they are the point at which one gives and one receives. This last sequence, I got in a dream once, so it's very special to me. Where exchange is happening. I see you, you see me, and something happens. But at the cellular level, where's the boundary? The room. At the atomic level, where's the boundary? The entire planet. As you move down at ever lower levels of scale, you get finally to the quantum realm where there is no boundary. One might call it the boundless boundary, the boundless body. Whoops. Which I got from Swami Brahmananda, who's sitting over here. I'm not good with titles, but these folks, they give me good titles. Joan Halifax in Upayas, I gave a talk like this, and she said, oh, no cell, no self. And that's true. So the boundless body, if we are all part of one boundless body, what's that like? In the realm of the boundless body, there's nothing to give and nothing to receive. Compassion. I see someone's hand stuck to a hot stove, I think, oh, the poor person, and I go pull their hand off. But I had to think about it and make a judgment and a decision. My hand gets stuck to the stove. There's no moment of thought because I'm one being. If you have this kind of wisdom as a deep experience, then compassion is just what arises because everything is just you. Thank you.